Hello everyone and welcome to my talk Focused LRP, Explainable AI for Face Morphing Attack Detection. I'm Clemens Seibold from the Fraunhofer Institute in Germany, and I represent a new method to analyze the decision-making process and feature activations of deep neural networks for the detection of morphing attacks. Let's start with a short introduction to face morphing attacks. A face morphing attack is a harmful use of a synthetic image that contains characteristics of two different subjects. For example, such an image could be used in an ID card or a passport, and in this way, two subjects can share their identity and one can travel or do business under different identity. Today, there's a large variety of freely available tools to generate such an image, which is called morphed face image or simply morph. The images that are generated in this way are proven to be able to fool even commercial facial recognition software, such that both subjects match against the morphed face image. Here you can see an example of a morphed face image. It's the image in the center, and the morph resembles the two different subjects that are shown in the image on the left and on the right. Our objective was to develop a framework that can highlight traces of forgery in morphed face images. The output of a DNN for classification is usually only a decision for a class, or rather a score for each class, but per se it does not provide an explanation about its decision. Inspired by the DNN interpretability method LRP, we developed focused LRP, compared it to LRP, and identified the strengths of our proposed method. The structure of my talk is as follows. First, I give a short overview on how a morphed face image can be automatically generated. After that, I present the DNN-based detector that is analyzed in our work. Subsequently, I explain LRP, a tool that explains which regions of an image are important for the decision of a DNN, and after that, our new extension Focused LRP is explained. Afterwards, a framework to evaluate and judge the relevance assignment by LRP and FLRP is explained. Finally, I conclude my talk with our experiments and the identified strengths of FLRP. Here you can see a pipeline to generate morphed face images that is usually used to generate them, also by freely available tools. To start it, we need one image from each of the subjects that the morph should resemble. In the first step, we calculate for each of these images the facial landmarks and transform the images so that they are aligned. In the next step, we blend the aligned source image using additive alpha blending. The result of this process contains visible ghosting artifacts around the silhouette of the head and the hair. To get rid of these artifacts, we insert the inner part of the face of the blended image into one of the aligned source input images using Poisson image editing, and thus we obtain the final morphed face image. Our detection method is based on a deep neural network and a pre-processing step to obtain a normalized input for the network. The input image is rotated and cropped so that the eyes are on the same height and only the inner part of the face is processed. Finally, the image is rescaled to a fixed size. This processed image is then fed into a DNN. In our experiments, we use the VGGA architecture, which consists of several convolutional layers that can be viewed as feature extractor, followed by fully connected layers for the classification. In our experiments, we trained the network as naive two-class problem, and the output classes are morph and genuine image. We had about 2,000 genuine images and generated the same amount of morphs. These images are split into a training set of 70% of all images, a testing set of 20%, and a validation set with 10%. And here just some details about the performance of the detector. The attack presentation classification error rate is 4.9%, the bona fide presentation classification error rate 2.6%, and the equal error rate 3.3%. Common interpretability methods for DNNs assign to each pixel in the input image a relevance score that describes the contribution of this pixel to the decision of the DNN. The relevance assignment can be visualized using heat maps. In this example and in the following, we use the Parula color map to visualize the relevance assignments for an image. Blue indicates no relevance at all, yellow a high relevance score, and green something in between. So in this example here, the specular highlight on the nose and the right eye are most important for the decision of the DNN. A method to obtain the relevance for each pixel is LRP. LRP propagates relevance that is assigned to one neuron in the last fully connected layer that describes the class back to the image. The relevance is propagated layer-wise from the last layer to the input image using a set of rules. These rules are designed so that LRP shows which regions in an image lead to an activation of the class by assigning to these regions large relevance values. Thus, LRP answers the question, which regions in an image lead to an activation of the class. But in terms of morphing detection, this is not always equivalent to which regions do contain morphing artifacts, even if we start LRP from the neuron for the class morphing attack. Inspired by LRP, we propose FLRP, a tool that answers this question, which regions do contain morphing artifacts. In contrast to LRP, it does not assign a start relevance to a neuron in the last layer, but to a set of neurons in the last layer of the feature extractor. These relevance values are then propagated to the input image with the same set of rules as used for LRP. By this concept and by choosing neurons that are artifact aware and thus have a high activation if the image is a morph phase image, our method focuses more on the question, where are artifacts that are detected or detectable by the DNN? For the selection of the start neurons, we are looking for neurons that are discriminative and have a large activation if the image is forged. To this end, we calculated the output of the feature extractor for all images in the training set. Then we calculated an activation threshold for each neuron such that below this threshold is the same amount of genuine images as morph phase images are above this threshold. Then we selected for each channel the neuron that best separates forgeries and genuine images. This results in 49 different neurons that we use to start FLRP. In order to evaluate the different relevance assignment methods, we extended a common approach based on substitution of relevant regions. First, the relevance is calculated for the input image of interest, and then based on the relevance, a fixed number of pixels with the largest relevance is substituted. Usually, these regions are substituted by a default value or values from a predefined distribution. In our scenario, and since the DNNs are always fed with aligned images or faces, this would create data far away from the data distribution that was used to train the network. So we developed a more sophisticated method. We use one of the aligned input image to get the color values for our substitution. Actually, we substitute the selected most relevant regions by the corresponding regions of the input image. The final image without the as relevant highlighted artifacts is then fed into the network, and the change in the decision making is analyzed to analyze the quality of the relevance assignment. We use this proposed approach on our morphed phase images with different amounts of substituted pixel and analyze the differences in the loss function of the DNN and the error rate in terms of APCER. For these metrics, we expect that the better relevance assignment method leads to a larger error. The differences between FLRP and LRP are small, but FLRP performs better even though it does not consider the classifier. In order to get a better understanding of the differences between the relevance assignment of LRP and FLRP, we analyzed the relevance maps more in detail and studied how similar the maps for LRP and FLRP are and where exactly the differences are. To this end, we calculated the transparency maps for a fixed amount of pixels and calculated for each image the normalized difference between the transparency map calculated by LRP and by FLRP. The results are shown in this histogram. A value of 0 means that the transparency maps are identical, and a value of 1 that they do not overlap. Even though they mostly overlap, there's a large peak at the other end. We analyzed these images and saw that the output for FLRP and LRP strongly differs for most morphs that are not detected or the DNN's decision has a low degree of certainty. In these cases, LRP often assigns most of the relevance to the part of the forgery that does not contain easily visible artifacts. But FLRP, on the contrary, does still assign relevance to these forged regions and thus highlights traces of forgery that are detected by the DNN. In this example, the image was falsely classified as genuine image, but it's a morph. It contains easily visible artifacts at the nose and the right eye. At the right eye, you can see that the specular highlights are somehow strange, and at the nose that there are some ghosting artifacts around the nostrils. However, LRP assigns most of the relevance to the genuine-looking left eye and no or only marginal relevance to the visible artifacts around the nostrils or the right eye. FLRP was still able to detect and highlight the traces of forgery. Here you can see another example where LRP and FLRP strongly differs. LRP assigns most of the relevance to the right eye, that looks quite valid, while the obviously morphed left eye only gets relevant assigned by FLRP. In this example, the DNN had a low degree of certainty in its decision. However, in most cases, LRP and FLRP show quite similar results as shown in this example. It shows a morphed face image and that was detected by DNN with a very high degree of certainty. Here, both methods assign relevance to both eyes and to the nose, and the difference is mostly in the strength of the relevance. So with FLRP, we proposed a new method that can highlight traces of forgery, even if the decision of the DNN is wrong or with a low degree of certainty. In these cases, LRP assigns relevance often only to genuine-looking regions instead of assigning it to easily visible artifacts. In other cases, LRP and FLRP perform quite similar, that there's no disadvantage in using FLRP instead of LRP for detection of morphed face images. In future work, we plan to study the effects of image improvement and image compression on LRP and FLRP. We also want to test our evaluation framework, LRP and FLRP, on DNN-based morph detectors that have been pre-trained with a complex multiclass pre-training. This complex multiclass pre-training usually leads to a very complex structure in the classifier and is difficult to interpret by LRP. We also want to extend our framework so that it can work without a reference image. I thank you for your attention and hope you enjoyed my talk.